And so we'll look at the last factor that will alter where equilibrium lies, and that is changes in temperature. Now, for changes in temperature, we've tweaked up our equation a bit. What I've done is that I've now added this term here on the back end, which is in essence going to be my change in enthalpy. What I am saying is that in this equation, when A reacts with B to produce C, we're going to have a change in enthalpy of positive 250 kilojoules per mole. That's like saying this is an endothermic reaction. So I stress that because when we're talking about changes in temperature, we need to recall that an increase in temperature favors the endothermic direction. Now, I know, you're looking at this, you're going, what do you mean the endothermic direction? What are you talking about? And so to help us with this, what I normally do is when we're working these out, I always stress when you see one of these LeChatelier's principle problems, and they're asking you for, the delta H is this or the delta H is that, I always remind everyone to draw some arrows. So I'm going to draw an arrow going from left to right. And then I'm going to draw an arrow going from right to left. Okay? And these arrows represent the direction in which my reaction is occurring. So right now, based off of the information that is given to us right there, okay, when this reaction proceeds from reactants to products, it would be fair for me to say that this reaction is endothermic. So going from the left side over to the right side, that would be an endothermic process, or the reactants require energy in order to make products. Okay? Now, if I were to reverse this reaction, in other words, if I were to flip this thing around, if I flip the reaction, I flip the sign, which means when I go from right to left, that is the exothermic direction. So in this case, endothermic left to right, exothermic opposite direction. If, sake of argument, I would have drawn this equation and told you that for this reaction it is exothermic and delta H is negative 250 kilojoules per mole, then I would have to change these arrows, right? I'd have to change what this says. Now, going from left to right, it would be exothermic, and then right to left, endo. That would be if my value was negative 250 kilojoules per mole. So let's go back to how we had it. And so the way we had it was we said that this was positive 250 kilojoules per mole, which means that it is endothermic going to the right. It is exothermic going to the left. Cool. So without getting into the why, because in order to understand the why, we need to understand thermodynamics, and we have not covered that yet. What we're going to do is we're going to stick to our rudimentary, cheap and dirty. And what we're going to find is this. For reasons that we will get to, for now, magic. But for reasons that we'll get to, when you increase the temperature, what you're going to do is that if it is endothermic, meaning if a reaction requires the input of energy, what you're doing is that you are going to alter the value of K so that K will now produce more of those products. In other words, without getting into the why, in this particular case, if you jack the temperature up, you increase the temperature, the value of K is going to increase. Now, how is that different from anything I've said thus far? Well, in all the other scenarios, when I did C over A times B, and I said that the equilibrium constant was 1, the equilibrium constant never changed, right? It was always, we got to make it back. We got to make it back to 1, right? Where it's something else, how to go back, right? So when we talked about all of my other equilibrium constants, the value for our example was always 1. But now, with a change in temperature, what's going to happen is that in this case, if you increase the temperature and that favors the endothermic direction, that means that my new value of K is going to change, and now my new value of K is going to be 2. or it'll become 3, or it'll become 5, etc., etc., etc. Changes of temperature are the only variables that will alter the actual value of an equilibrium constant. So you want a new equilibrium constant? Change the temperature. And if you think about it, we can kind of explain that what we learned with our kinetics. We know that every time we change the temperature, a reaction happened faster. The question was it the forward direction that happened faster, or was it the reverse reaction that happened faster? And so the same is still in play here. Once we understand thermodynamics, we'll see how that comes into play and how all of that will come together. But for now, this cheap and dirty will work. What's the opposite of this? Well, if you decrease the temperature, then what we're going to find is that a decrease in temperature is going to favor the exothermic direction. And so in that case, if let's say we were to take this reaction and we were to now decrease the temperature, we're going to favor the formation of more A and B, or to say that differently, my value of K is now going to decrease, and so maybe as I increase the temperature, it's going to become 1/2, or 1/4, or 1/8, etc., etc., etc. Okay? All of these factors are true, all of them work, and this is how we can explain how LeChatelier's principles and temperature will alter my equilibrium constant. Okay, not my equilibrium constant, will alter my equilibrium. It is a change in temperature, and only said change in temperature, that will alter and will change the actual value of the equilibrium constant K. Anything else, you're leaving K alone, you're altering the reaction quotient Q.
So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.